Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be diving deep into some diagnostics and repair for the Macintosh SE30. In last week's video, I started troubleshooting this particular Mac SE30 motherboard, and it had suffered some catastrophic damage that unfortunately I caused, and I think I repaired at least some of it. If you haven't seen that video yet, I'll put a link in the description below. I highly recommend you watch that first before continuing on, because I'm going to have some spoilers here in just a moment. So for this motherboard, what ended up happening is I replaced the caps, and one of them was accidentally shorting the 12-volt rail to data line 31, and that 12 volts going into what should be a 5-volt line took out at least the CPU, the ROM chip, and the sound chip on this board. I was able to replace those with other spare parts I had, and I also went ahead and replaced this VIA chip, the 6522 up here, because that was getting really hot when the 12 volts was going through the entire motherboard. But at the end of the video, after troubleshooting quite a bit on this board, I was totally stuck. And that's because the diagnostic ROM that was running here in the main system ROM is detecting some type of issue on the board, and then it stops the machine, it halts the computer, and it plays the sad Mac tone. Now, unfortunately, this screen's not even initialized yet, so there's no error codes to be printed, and the sad Mac tone is just the generic little tune that's played, so it really doesn't give me a lot to go on. And if you're a regular viewer of my channels, you'll know that it's not my style to just willy-nilly start replacing chips on this board. I do have a spare motherboard. It's a Macintosh 2 CX motherboard with battery damage, and I could replace all the chips on this board, but I'd much rather try to figure out what's actually wrong with this thing first before I do that. That way I'm not taking the shotgun approach, which is something I really hate doing. So between the making of the last video and this video, I have done a lot of research and I've been very busy. I have stumbled across some incredible information which should be a huge help to anyone trying to troubleshoot these types of motherboards that have some type of damage where you don't know what's wrong. And in this video, I am going to explain exactly what I've been working on, what I figured out, and then we're going to try to see if I can get this motherboard, or maybe not this motherboard, but another broken SE30 motherboard working again. So without further ado, let's get right to it. So I have lots to cover in this video, and let me first talk about what I meant about maybe not repairing this motherboard. This is the one I worked on, the last one that had the 12 volts through all the different rails here. This board is still exactly like it was where we left off in the last video. Well, the only thing I did do is I had removed this chip here. This is the video RAM chip that was hit with 12 volts. So I took it off the board in the last video, and I've since resoldered it back on while I put some pin headers on there, so it's actually in a little socket there. But otherwise, I haven't really done anything with this board. It is still not working. Now, the other board I alluded to, as in the one that I think I'm going to try to repair in this video, is this SE30 motherboard. We can tell them apart because it's got white SIM sockets versus this one, which has black ones. Now, this board was another one that I came across that I didn't show in that second channel video where I was troubleshooting these different motherboards, the different SE30 motherboards I had, and this one also has a fault. So this motherboard, I don't think has any kind of faults when it comes to 12 volts going through the voltage rails. You can see that this thing has been recapped, and it wasn't done by me actually, but these are tantalum caps that are on here. But this thing definitely had leaky caps at some point, and it was obviously cleaned because it's super clean. But this motherboard has some really interesting faults. The main one, of course, when you plug it into power, you get a sad Mac tone, just like the other one, the one that got damaged with the 12 volts. But the other weird thing that's happening with this one is the video, at least through the RGB to HDMI, is flashing repeatedly, which is kind of strange. I haven't actually tried this inside an actual Mac chassis, but my assumption is because the RGB to HDMI is kind of unhappy with the video signal, but we're seeing the video signal, it just is flashing. It means there's something going on with this board besides the sad Mac tone. Now, just like last time, I'm using my same little test setup here. So this is an old Mac SE power supply that's had the high voltage stuff removed from it, no flyback and stuff like that. I have a little PicoATX power supply plugged in here, so that's 12 volts. I have an RGB to HDMI hooked up on the other side of this cable here, and that is coming right off the motherboard, which of course comes from the signals that come right from the motherboard. There was a little IC that's underneath this little blue tack here originally. That IC is what bridged the various sync and video signals into the CRT section of the board here. With that IC removed, I just simply installed these pins here that go to this, which of course is what's plugged into the RGB to HDMI. This power switch here just turns on the PicoATX power supply, and if I plug this into this motherboard here, this is the new faulty one, and I plug in a speaker. I have a different speaker to use this time. It has a little bit longer of a cable, so I can keep that out of the way. If we turn this thing on, there we go. We're getting the same Sad Max slow tones that this other one was getting from last week. So I'm just gonna move this one off the bench right now. These are the bad chips and stuff that were on that other one, so we don't need these. These are some memory sticks. I don't know if they work or not. And a warning for anyone who doesn't like flashing, I'm gonna turn this broken machine back on and you can see what it's gonna be doing. So there's a flashing there happening on the screen, and what we can see behind the flashing though are the usual bars that you see on these Macintoshes when they're not posting. Now there's a particular term for that pattern, like Siamese Mac or something like that. I don't know what that is all about, but basically what's happening when you're seeing those types of stripes, and also that gray pattern we were seeing on the last motherboard, is that the video RAM is not being initialized. Now this motherboard here has these TI video RAM chips. These are dual ported chips, 4 bits wide each. Dual ported means that there are 4 bits that go towards the CPU, and there are another 4 bits that face the video generation circuitry, which is this stuff here. That means the CPU can read and write from the video RAM at any time without having to slow down and wait for the video generation circuit to be pulling and refreshing the RAM as it displays it on the monitor. If your Mac SE has these particular TI RAM chips on it, when you first apply power to the system before those RAM chips are initialized, meaning they're erased by some ROM code, then they default to this pattern of white and black horizontal bars. And then what happens is if the motherboard passes its main diagnostics that are coming out of the main system ROM, that's on the ROM sim right here, then it will kick off the video initialization based on the video ROM chip here. Think of it like a video card that's plugged into a Macintosh or a PC for that matter, and the BIOS code or the ROM on the system is booting up the system, and once it feels it's ready, it will then kick over to the video ROM that's on the card or integrated into the motherboard in the case of the SE30, and then that goes and initializes the video. In the case of the SE30, what the ROM does is it will draw that checkerboard pattern that you're used to seeing on a black and white Macintosh, and then eventually you'll get the mouse pointer, and I think it hands control back to the main system ROM, and then it boots the system. Anytime you're seeing that particular pattern with those bars on the system and they stay there indefinitely, that's happening specifically because the video RAM is just not initialized. It's in the power on default state, and even though the video subsystem is not initialized per se, like the ROM hasn't even run, these PAL chips that are on the motherboard are still doing their thing and they're displaying what's ever stored in the RAM. Now this particular board here, this is the one that got the 12 volts. If you remember when I turned this one on, it didn't have those bar patterns. It actually had more like a gray checkerboard pattern, but kind of like with a distinct pattern of itself in the checkerboard pattern. And that's because this uses NEC branded chips. Seems that there are 2 companies that make chips that are in use on these motherboards, the TI ones that draw the horizontal bars, and these NEC chips that give you that gray pattern. The reason why we're seeing a pattern that doesn't change and we never get the mouse pointer or that nice solid gray pattern on both of these motherboards is exactly the same thing. They are both failing their power on self-tests, and the ROM, this one here, never gets to the point where it initializes the video ROM. Now, I have tested on a working motherboard, I have one down on the floor there. If you pull out the video ROM from this machine, the Macintosh SE30 still boots. It doesn't actually have a problem with the fact that there's no video circuitry. It's kind of like a Macintosh 2 if you don't have a video card plugged into it. I guess the ROM is okay with it working that way, and it just tries to initialize something that's not there, and it just continues on its merry way. But of course, if you pull out the video ROM, the system will give you a normal boot up sequence, but you will not get any video, and of course you're left with that same exact pattern. Now I'm mentioning all this because I had a number of comments on the video, on the second channel video for this motherboard and the main channel video, where people were asking if I had gone to watch other people's troubleshooting steps for their Mac SE30s having the same pattern. That's not in and of itself a bad suggestion, but the thing is, if you caught what I just said, the video is never getting initialized because the SE30 motherboard is failing its initial diagnostics. And as far as I'm aware, there are a whole bunch of different diagnostics that run, and any of those things failing are going to keep the video from initializing. So in other words, there are many different types of failures that can happen on these motherboards that can result in the video not getting initialized. The analogy I make is it's much like a car. If someone goes to you and says, "Hey, my car doesn't work, what's the problem?" Well, unfortunately, that's just not enough information because your engine might not run on your car because it's out of gas, or many other types of failures. And with the Mac SE30 video, it's exactly the same. There are many causes of the video not getting initialized. And unfortunately, just watching other people's videos where they fix that problem really doesn't give me any particular clues because, well, it could be anything that's wrong that's stopping the boot process. Now, at the end of the last video, I mentioned that I was sort of stuck because the ROM wasn't giving us any useful information about what the failure was. And I really wish someone had done a disassembly or something like that of the Macintosh SE30 ROM, which is the same as like the Mac 2 and 2X and 2CX. Now there's a whole bunch of different machines that use the same type of ROM, but it doesn't seem like there's been any kind of disassembly that's ever happened with that particular ROM. There were also a number of comments of people asking me if I had read some inside Macintosh book. I think it's some technical documentation that Apple published way back in the day with the Macintosh 2, and I had never read that, but I went and checked it out after several people recommended it. It's a several hundred-page document. And unfortunately, in typical Apple fashion, it's way too high level to actually have any useful information. There was a block diagram in there and a memory map, which, maybe that's kind of useful, although it's kind of generic and it wasn't specifically for the SE30, it was more for the Macintosh 2 and the other older Macintoshes. But when it comes to the boot process and the diagnostics that run when you first turn on the machine, it just sort of glazed over that whole section, just said, oh, it runs some tests, and if a failure happens, you'll get a sad Mac tone. And that's pretty much all it said. So nothing really helpful there as to try to figure out what's keeping this machine from booting. Well, both of these machines now. So what I did next is I reached out to some members of the Mac community asking them if there were any tools available for a regular person like me at home in their basement to be able to diagnose these computers. Well, what came up was Apple had a special dealer-only tool called the TechStep, and this was something that was contemporary when these computers were being sold. And this box that Apple had available for their dealers, I guess, I don't think this was a consumer thing, plugged into your Macintosh through a whole bunch of cables. So you plugged into all the different ports on your Mac. And then what you did is you powered on your Macintosh, and with a special ROM inside your TechStep device, which had a little screen and a keypad, it would actually force your Macintosh into a diagnostic mode where the TechStep would then take control of the machine and be able to run a whole bunch of diagnostics on it and figure out potentially what the problem was. And it would display any errors found on a little screen on the TechStep device, and it had a way to download reports off of the TechStep onto another working Mac where you could read a more detailed report of maybe what was wrong. Now, as far as I'm aware, this tool is very rare, and that's because even Apple dealers typically didn't do circuit level repair of a machine. So they didn't really need to know, oh, a particular chip was bad or something like that, because a dealer would never be doing that type of repair. Apple never offered any spares for the chips that were on these motherboards. They simply offered entire motherboard replacement. So anytime there was any kind of failure on here besides, say, a RAM problem, Apple would say, swap out the entire motherboard. And if the board was under warranty, the dealer would get a new replacement board from Apple, and the old one would have to be sent back to Apple. As far as I'm aware, Apple had very tight inventory control of their replacement parts as well. So if you were sent a replacement motherboard as a dealer to put into someone's computer, you would be charged a heavy sum if you didn't send back the broken part back to Apple. And I'm pretty sure that's even if the motherboard and the computer was out of warranty and the end user was paying full price for a replacement logic board, as Apple called it. You still had to send the old one back. And that's one of the reasons why there really aren't a lot of spare parts for these machines. If any of these custom chips on here go bad, well, unfortunately, we're going to be taking them off of other boards that maybe have had catastrophic battery damage, like that Mac 2CX I showed in the last video. And that's because these boards just weren't collecting dust in dealers' back rooms to be, found on the secondary market. Apple took them all back, and I'm assuming that they sent them to repair centers that maybe had spare parts, and then they were repaired and put back into refurbished machines. Anyhow, some of these TechStep tools did make their way into end user hands, obviously, after these machines were no longer contemporary. And as far as I'm aware, when they do come up on eBay, they sell for absolutely ludicrous amounts of money. Huge sums of money. And that's because they're very rare, and to someone who's trying to troubleshoot these types of machines, they're very valuable. Now, it turns out that the community has gotten together and replicated the TechStep. So I don't know if it's like a full reverse engineering, but at least they've reversed the PALs and whatever custom chips are in there and recreated the TechStep. And so there are new versions available, including from KMag Vintage, who ironically were the folks that gave me that adapter board for the SE30, which I was testing in the second channel video. They sell that TechStep. The replicas, though, are still pretty costly. I think $400, $500, and maybe that's not without all the cables and stuff that you're going to need to use it with one of these Macs. That's a pretty hefty sum if you're someone, even like me, who's just a hobbyist, who doesn't repair Macs for a living, for instance. So it doesn't really make sense for me to go out and buy a TechStep, and especially because what kind of an interesting video would that be if I use something like that to repair these boards? And that's not something that most people have, right? That's what I try to do on my channel, is show that it's possible to repair these things without the super expensive tools, using cheap parts like, you know, this $80 oscilloscope here, for instance. All right, so finally, with all that backstory, that brings me to where we are now. And while I was looking for more information on this TechStep, which seems to communicate with Macintoshes over all the ports, but primarily the serial port, the TechStep activates some kind of Apple diagnostic mode that's baked right into every single one of these machines. And the TechStep just uses a bunch of commands to talk to the machine over the serial port to run these various tests. That's like a eureka moment to me. There is no reason why we need to use an actual TechStep device to do these diagnostics. Why can't we just use any computer hooked into the serial port of the Macintosh? We just need to understand what kind of protocol is happening between the TechStep device and the Macintosh so we can run those tests for ourselves. And that brings me to this document right here. This is something that has been archived by the Wayback Machine, but the original is actually offline. The last version that was available was from sometime in 2021, but it looks like it actually hadn't been updated since 2015. So this had been kicking around on the internet for quite a long time. And I was first clued into the existence of this document just by happenstance. I was just reading through a whole bunch of old posts on some old forums from years and years ago about the TechStep, and it pointed to this document. And I was really sad that the link that was on the forum post didn't work anymore, it just went to a 403 error. But the Wayback Machine comes through again. Well, and here's the document. And what this looks like is a breakdown of the protocol that the TechStep uses to talk to the Macs over the serial port. And it means that we can actually run these commands ourselves. We don't need a TechStep to do a lot of this diagnostic information. Well, and unfortunately, what's in this document here isn't really complete. I think this was just someone's best guess at how it worked, probably by taking a TechStep, hooking it up to a Mac, and snooping the serial bus. But what this is an incredible start, and I was able to do a ton of testing using the information that's in here in a working SE30 motherboard where I created faults by doing stuff to it, and I was able to kind of reverse engineer more about how this protocol works. And on this new motherboard here, not the one from last week, but this one here that has the flashing video output and the horizontal bars, I think using commands from TechStep, I'm able to kind of understand what is freaking wrong with this. Let's fire up the terminal emulator and get connected up to this motherboard so I can show you what I have found. Okay, so first things first, we need to get connected to the serial port on this motherboard. And it turns out, these are the two ports right here, that it is the port on the left here, the one closest to the sound jack, that actually is providing the diagnostic serial connection to whatever's attached to it. Now, I just have a regular Macintosh serial cable here. It goes from the little mini DIN to a standard 25-pin D-sub connector. And this type of cable is designed to work with something like a modem. It's not designed to plug into another computer. To facilitate that, I'm going to be using this, which is a lap-link serial cable. This is nothing more than a no modem serial cable that happens to have a 25-pin and a 9-pin on both ends. And back in the day, cables like this were used to connect up two PCs to each other and run software called lap-link to transfer files. Before we had things like flash drives and even before that zip disks, it was very difficult if you had a 40 meg hard drive and you need to copy all the files from that one machine onto your new computer. So this software called lap-link allowed you to just do it over serial, and while you're running at 115,200 bits per second, that was still fine. You would just connect it up, select all your files, start the transfer process, and then come back the next day, and all your transfers were done. I still have this cable because I find it immensely useful just by the fact that it's got, I don't know, both types of ports on the back here. And all I need to do is take this Macintosh serial cable here, connect it up to the 25 pin on one end, and then plug this other end into any kind of PC. You can use a USB to serial adapter, or in the case of my lab PC right here, which is even a modern Ryzen 5600, I still have serial ports on it. So I can just plug this 9-pin connector right into my serial port, and we're in business. So it might vary which of the two serial ports is in use on which Macintosh, but on the SE30 at least, it is this one over here, which is as close to the edge of the machine as possible. And for connecting up to this bad motherboard, I'm going to be using this free program called TerraTerm. And the settings you use are 9600 bauds, 8 bits, and we have to use 2 stop bits and no flow control. In addition, I'm going to add some transmit delay, 1 millisecond per character, and that's just if I'm pasting commands into the diagnostic ROM. I found that having a little bit of delay there really helps. So we just hit new setting, and now I'll just turn on the Mac. Okay, so we have a sad Mac sound, which you might see on the serial port. We didn't really see anything, and you might think, okay, well, it's not working, right? Well, it actually is. I'm just going to grab my keyboard here and type *A. And even though we're not seeing anything on the screen here, we are now in ASCII mode and connected to the Macintosh. Now, if we take a look at this document at the commands we can type, not all of these work on the SE30. I think this was created based on a much later Mac that has a bigger ROM and more capabilities. But what I did is I put it into ASCII mode with the *A command. And all the commands you do type here are case sensitive. They have to be uppercase. Now, if we take a look at the document here, we can see that *5 says start boot message. And if I go back to the terminal window, we type *5, what this is going to start doing is it's going to start printing this message over and over again. Now, one thing is it's telling us the machine is alive here, and it's saying Apple, and then we're getting this code here with F's and an E at the end, and the number 1. If we go back to this document here, there's a machine identifier section that mentions here that the number 1 in that string we were seeing is the Macintosh 2 series. And yeah, the SE30 is a Mac 2, really just in a compact Mac shape, and uses the same ROM as a whole bunch of different Macintosh models like the Mac 2 CX and stuff like that. I'm assuming here, because this shows the SE, the Plus, the laser writers, the portable, the 2CI, and the 2FX, these all have different machine identifiers with the same diagnostic compatible ROM that ostensibly uses the same commands as what we're about to look at right here on this Mac, and the TechStep itself communicates with them. There's also the Classic, the 2SI, the LC, and then there are these Quadra machines, and I guess down here at O, there's some other ways to query the machine identifier beyond the O. Now, what this is doing is repeatedly printing this message. It's scrolled off the top of the screen, but if I type *S, that's going to stop it from scrolling. What we're looking at there with that series of numbers and letters, though, is the response code, which, oops, it's not in ASCII mode, so I do *A again. So we do *R, and that's the response code. Now, anytime you run a diagnostic test manually based on what's in this document here, or you first power on the machine and it gives you a failure code, like this has the sad Mac automatically, this is the response code that's coming back from the diagnostic ROM. It's actually literally telling us what is wrong with this machine. Now, we have a few different parts to this particular response code that are relevant to what's happening with this machine. The first one is this last letter E. Well, actually, these last 4 digits that end in an E. If we take a look at the document here under return section, the last value, which has that E there, is from this list, as far as I'm aware, and it says data bus test failure. So this particular Mac is stopping and failing on a data bus test error. And then this part, which is all F's except for 2 zeros at the beginning, is the actual status that is relevant to that particular failure code. Now, I know what I just said there doesn't make a whole lot of sense, and when I first started looking at this, I didn't understand what the heck it was talking about. But we can run some tests manually to try to uncover what's actually going wrong with this machine. Now, this document has a lot of good information, but unfortunately, what I found through testing the working SE30 motherboard is that a bunch of it's not really relevant to the SE30. Like, these are things that don't even run or work or are applicable to this machine. But beyond that, when it comes to the critical tests that you can manually run, and here's a list of them here, size, memory, and data bus test and stuff like that, I don't even think this stuff is necessarily correct, because I think Rob Braun, who was creating this document back in 2015, was kind of guessing at the functionality of this based on communications that he observed between the TechStep and a Macintosh under test. And it was not an SE30, so I think some of this stuff isn't even applicable, but he was sort of guessing at maybe the parameters that are being sent and received to try to figure out what they're doing exactly. So we can look at this list of critical tests that we can run on any Macintosh that's plugged in and in this diagnostic mode. We have size memory, we have a data bus test, which is very similar to that failure which we're seeing when the machine is first powered up and we got that response code. There's a mod 3 RAM test, an address line test, a ROM checksum, another RAM test, another few RAM tests, and then a size video RAM. Well, unfortunately, other than this text at the top here, it doesn't really talk about what you need to do to run these tests properly. Well, luckily, I spent pretty much all day today with the working SE30 motherboard plugged in and trying to run these tests and figure out, to the best of my knowledge, what exactly these various tests do and the right parameters you need to send to the tests to actually initialize them or initiate them. And because I was creating a whole bunch of notes as I was running through these tests and trying to figure out how they work, I just created a whole new document to describe how this works, especially because this one's offline and it's on the Wayback Machine. And this right here is that document. It's a Google Doc, and I'm gonna, of course, put a link to it in the description below, so it's publicly available to anyone who wants to look at it. And I took all the information that was on that original document that was on the Wayback Machine, and I transferred to this spreadsheet here on these various tabs. But I added a lot more information that I found out as I was working on it. So let's go through the tabs on the spreadsheet. First one is just mostly information I copied from the other one, including the original Rob Braun information. And if you hover over that, there's a link to that original Wayback Machine document. But I also have my name with the new date here, and Dave Gitler was helping with some test code that I was running inside the Diagnostic ROM. Yes, you can actually run your own code, which you upload over serial into the Mac and then do stuff with that. And some of the highlights of this first tab are, yes, all commands need to be in uppercase. You have to remember that when you're interfacing to this thing manually. It will ignore your commands if you don't type them in uppercase. And the other weird thing is, and you might have noticed that as I was typing in the serial console there, is it doesn't echo back anything you're typing unless you've typed stuff wrong. So as you're typing correct commands, you don't get an echo back. Now here's the command tab, and it's pretty much just a copy of what was on the other document. I don't think I really added too much stuff here, but I did add an extra column here to say whether this command works on the SE30 or not. So the green ones do, but the red ones do not. So on the other document, you might have noticed as I was scrolling back and forth, there's some non-critical tests to run a bunch of additional tests. And none of that stuff works on the SE30 at all, at least not in the way described in this document. Maybe the TechStep plugged in directly to the SE30 does issue some other secret commands that we don't know about because they weren't documented here, but I don't know what they are, and the ones that are listed on this document do not work. And when I say document, I mean these non-critical tests. So there was a command *N for non-critical tests, and then it listed on the other document, and now here, all of these various tests you can run. Well, the *N command doesn't work on the SE30 or any other machine that uses the same ROMs as the SE30, so therefore none of these tests are actually available to us, at least not in a way that we know how to use them. Now what does work is the *T command, or the critical tests, which are these commands here from the original document. The problem is, as I mentioned, other than the data bus test here, which tells you to use the *O command to load a parameter before you run it, none of these other ones tell you what they really do or how you pass parameters to them. So that's what I did a bunch of work trying to figure out, and I've written that here in the notes for each of these tests. Hello, it's just Adrian here from the future, and I'm editing the video and I just wanted to add a little extra context to this document. I've actually gone ahead and updated it with some additional information, including more detail on how to use these critical tests. None of my misunderstanding about how these tests work actually affects any of the diagnostic outcomes of this video and the next part, but I just wanted to let everyone know that this information is a little bit more correct now if you go to look at this sheet and try to use it on fixing a machine. Okay, back to the original video. So for the data bus test, which was documented on the other document, you have to first load a value, which is the address you're going to test, by using this *0 command. And here's an example, *01122333344. Sorry, I added too many digits there. And then when you run that test with another parameter, which I'll show you in a second what it looks like, that will test that particular address for a data bus error. Now for these other tests like this mod 3 RAM test, this on the SE30 doesn't seem to actually test anything. And all it seems to do is fill up the entire memory with these repeating values. See all these 32-bit strings right here? It just repeats those over and over again and fills up the entire memory for it. It doesn't seem to actually do any kind of testing that I can tell, and that's because when you run it against a particular part of memory and you read back the results always just all Fs. No matter if you're testing against memory that's good and there, or bad, or whatever. It just doesn't seem to do anything. But at least it fills up memory, so that's kind of useful if you're just trying to see if the RAM is able to be filled up quickly and then you can read it back. There's an address line test, which I actually didn't do any testing on, so I don't know if that does work or not. And then there's this ROM checksum. I didn't test that either. And then there's something called the Rev Mod 3 RAM test, at least on the original document. And on the SE30, that just crashes the machine every time you run it. No matter what you do with it, it just causes the machine to have a sad MAC tone. So that doesn't work. But then there's this test here, which if I scroll back over is test number 6. It's the extra RAM test. And this one does seem to work. And the way you use it is you load a start address into a CPU register using the *0 command, and then you set the end address using the *1 command. And if we go back to the original document here under *0 and *1, it just says load A0, load A1, takes a 32-bit argument, which is first loaded into register D6 and then A0. So it doesn't really tell you what those are used for, but what I found on the SE30 is that *0 sets the start address for the RAM test or any of these tests, and that *1 sets the end address. And the syntax is always the same. It's like this. You put *0 and then the 32-bit address for the start, and *1 and a 32-bit address for the end. And the extra RAM test here, when you run it, it absolutely does test the memory, and then the response value that you get back is actually telling you which bits are in error. So if you're testing a whole range of RAM, if there's a bit error somewhere in there, you're going to get a 32-bit address back as a response bit when you hit *R, and in there it will tell you which of the bits is bad. And this is a 32-bit machine, so it's going to give you a 32-bit response. And if you take the hex value and you convert that into binary, you will see exactly which bit is in error. And you can specify a start and end address that's smaller and smaller to try to zero in on where the bad memory is. Because if you have a motherboard that has, say, 1 meg sims on it, but you have 8 megs total, you have 2 banks of memory, and you have to figure out where in that 2 banks of memory your particular error is. And you can use that particular RAM test to test the video memory, and it will tell you which bits are in error in the video RAM as well, which is very useful because if you have a problem with your video memory, you're not sure which chip it is, well, you can use the schematics to figure out which data bits go to which chip, and based on the diagnostic test, it will freaking tell you which bits are bad. Now going back to the list of tests here, there's a mod INV RAM test, and from what I can tell, it does nothing. So it's either not that, it's some other test that I don't know what it is, but no matter what you do with it, anytime you run it, the response is always all zeros. So that's kind of useless. And on the original list of tests, there was size video RAM, which that does not work on the SE30 at all. If you try to run that test, you get back a question mark, which is the same thing you get back if you try to run any command that doesn't exist. Now, I mentioned when you're running these tests, and I haven't even shown you the syntax for running them. It's like a long string of characters, but there's a bit mask for the last part of that command you're sending that has these things here: stop on first test, or loop on failures forever, or even boot after test is done. I don't think these actually work either on the SE30. I tried sending these or setting these bits, and it didn't seem to make any difference whatsoever. I thought it'd be kind of fun if I could try to force this computer that's not running to boot up if I just ran a diagnostic test successfully, but that doesn't actually work, at least not that I can figure out. Now, when it comes to setting those ranges with the *0 and *1, as I mentioned before you run the RAM test, these are some examples here. So 32 megabytes of RAM, you do *0, and then you type all those zeros, and you would type *1 and 1 FFF, and that's the top of 32 megabytes. And here's an example of 1 megabyte and 64K of RAM, just the first 64K of RAM, and even the SE30 video RAM. The video RAM lives at this FE000, all those zeros, and it's 64K in size. So that's how you would test just the video RAM. You issue these two things before you run the test commands. Now, I did copy over the machine identifiers, even though it's not particularly useful. If you're working on a machine, you kind of know what it is, so it's no big deal. Non-critical tests, they don't work on this machine, but they're just here on the spreadsheet for anyone who's looking at this who maybe has a machine where they are used. And then I copied over the information on the response codes. Now, this is what I was talking about when it comes to the error when you first boot the machine. Like this machine is doing. When we first turn it on, we get a SAD back immediately, and that gives us a response code which we can look at. And remember, we took a look at what it was. It was 00FFFFFFF, this part of it right here, and E. We go back to the spreadsheet here. Remember, as we looked up already, E is a data bus test failure. Now, when it comes to decoding what those Fs and the zeros mean, I did some testing on a working SE30 motherboard, removing memory from the machine, which when you have memory removed from a Motorola 68000 machine, what happens is you get something called a bus error anytime you try to write to memory or read from memory that doesn't physically exist. Unlike a 6502, which doesn't really know if the RAM is there or not, it just reads and writes to the memory whether it's physically there or not. 68,000 base machines can tell if there's something there or not. So what this data bus error is telling us when we turn this computer on is that the CPU is not able to read and write from some of the data bits on this motherboard. Now, I put some examples of response codes on the spreadsheet, but I'm going to copy this one here and we'll paste this in right there underneath the other examples. The first one on this list here is 02, all these zeros, and then FF16. What that one is you get that if you're turning on a Macintosh and you push the programmer button very quickly after you power it on or reset the machine to cause it to crash. So have you ever noticed when you turn on a Mac 2 or a Mac SE30, you hear the nice bong to say it's turned on, you hit the programming button and it will go and it'll play the sad Mac tone. Well, what that's doing is actually forcing the computer to kind of crash and go into the diagnostic mode. And if you do that and you look at the response code, you're going to get this one right here with 02 and a bunch of zeros and then FF16. That is not on this list of potential codes, right? But I added it at the bottom. NMI, non-maskable interrupt, or the programmer button was pushed. This in and of itself is not an actual failure or a fault. That is just the code you get when you force it to go into diagnostic mode. If it goes into diagnostic mode like this machine on its own, we're going to get one of these codes. And all these examples I have, because that's all I really have for power on errors, are these ones with the E, which are these data bus errors. Now, the bottom one here are errors we're getting on this motherboard, but these other ones are ones I got by pulling the RAM out of a working motherboard. When I pulled all the RAM out of the motherboard and I had 0 RAM installed, this is the one we got. It's basically telling us the error code is 000E, and that's the data bus error, as in RAM doesn't exist when the CPU tries to read or write to it. And the bits that are in error are all of them. All these Fs is a 32-bit sequence. And if we bring up the calculator here and we put in the error code that we were getting, which is all Fs, there's the binary representation of it there, and it's 32 ones, which is telling us that all of the bits are in error. Now, when we take a look at the code we're getting now on this machine, it's 00, the leading zeros are missing here, and then all Fs. And if we switch to this mode here and we put double word, which is 32 bits, and we take away these ones here, what you can see is of all the 32 bits on the 68030, the bits that it's saying are in error are from 0 all the way up to 23. So the first 24 bits, but it's telling us that the last 8 bits are fine. And that's from 24 to 31. If you remember from the diagnostics I did on the other motherboard, the one with the 12 volts on the data line 31, we found that all of the 8-bit peripheral chips that are on that motherboard are connected only to D24 through 31. The way the 32-bit Motorola chips communicate with 8 and 16-bit peripherals is they either use the very top 8 bits or they use the top 16 bits. That's the way the designers of 68020 and the 68030 and 68040 wanted you to do that communication. It's kind of a requirement, actually. So it's kind of interesting to me that it's telling us here with this response code that it's that top 8 bits that's working and the rest is not. Now, when we look at this motherboard, there are 4 SIMs installed, and each one of these 8 bits wide. And I happen to know from looking at the schematics that this SIM here is connected to data bits 0 through 8. And then this one is the next 8 bits, and this one, and so on and so forth. This top one here is the one that's connected to data bits 24 to 31, which is what it's telling us is able to be written and read from by the CPU. Now, I happen to know, just because I've been working on this, that this memory is all good. This memory works perfectly. I can swap these around and the error will not change. I can put different memory in, like this RAM right here, and we're gonna see the same thing. So if you think about what might be going on with this, maybe there's a broken connection between the SIMs, these lower three, and the CPU, so it's not able to read and write to those data lines. Now, if we had a motherboard that had a bus transceiver that existed between the RAM and the CPU, like say they were 245 bus transceivers, maybe 3 of those were bad, or maybe the logic that controls those chips were bad, maybe it got damaged by some leakage from a capacitor. But I talked about this in the last video. The Macintosh SE30 does not use bus transceivers anywhere on the motherboard. They are supposed to be used on cards plugged into this expansion slot, but anything that's on the motherboard itself is just directly connected to each other. So the CPU is connected to all the peripheral chips. If they're 8-bit chips, it's connected on those top 8-bit lines. But when it comes to the ROM socket and the RAM, all 32 bits, well, 32 bits from the ROM socket are connected directly to the CPU, and then 8 bits for each of these SIMs is connected directly to the CPU. There's nothing in between the CPU and the RAM. It's just, this is a direct connection. So it's very unlikely that all of the data lines that go to these 3 lower sockets are bad. That would be way too much. Maybe if one of them were bad, I could see it. But all of them, no, not likely. And the next thing to think about here is that we know the 32 bits on the CPU is working because the ROM sim is communicating to the CPU through the 32 bits, and the system is booting. I mean, I know it's not booting all the way, but we're able to interact with the diagnostic ROM, which means that the CPU is communicating directly to this 32-bit ROM. So we know there isn't a problem with the CPU and the 32-bit data lines. So it's a weird failure that the diagnostic ROM is telling us the CPU can't talk to these lower 3 SIMs. Let's plug this back in and play around a little bit more. All right, let's finally get to running a few of these tests. Now, what I went ahead and did to help you run these, it talks about how to do it up in the copy right here. That's from the other document. But I've actually put some examples of how to do this stuff right here on this examples tab. All right, so with the system booted, the first thing you always have to do is type *A to put it in ASCII mode. Now, one of the things that you can do is hit *R. Oops, and you want to make sure you're doing it in uppercase, *R, and there's the response code, and we're getting that same exact error about the bus error that we're getting when we turn this machine on. Now you might want to clear this if you're going to run further tests, because I found as you run further tests, it doesn't always erase what was in the response code before, it just kind of ands it with what's in there now. So to get rid of it, you type *4, and now if we look at the response code, now it's just blanked out. Now we can also type *3 to disable the MMU. I don't really know if you have to do that anytime you're doing memory tests on this, but I saw that option there and I figure it's probably a good idea to do it just in case it might cause any kind of issues. So the syntax for running these critical tests is like this. *T, then you have 4 digits, which has to do with the test number itself. Then the next 4 digits represents the number of times you want to repeat the test, and I guess you can do it up to FF times, so 65,000 times. And then the final 4 digits seem to do with some kind of an option code for the particular diagnostic test. This is undocumented, there's no information on what the different codes mean, but I found that rather running it with the last 4 digits either 0000 or 0001 seem to make the test work perfectly. So back on the critical test page, we can see here that test number 1 is the data bus test, but we can also run test number 0, which is to size up the memory. So what I'm going to do is I'm going to add an extra column here to the test or critical test list, where I'm actually going to have a test sequence you can just copy and paste directly into your buffer so you can run these particular tests. So I'm just going to paste this in here, and you don't see an echo of what you type when you're connected to the Mac, but what it will do is when the test completes, you'll see the *T that prints there. Now we can type *R to actually get the response code. Now remember, for the response codes, that first 32 bits is the relevant section that we're interested in. And if we take the programmer's calculator here and we take that value and we paste that in, of course in hex mode, and you can see here that the amount of memory that's detected, which is in bytes by the way, is 1 megabyte total. Now I know that it's responding in bytes because when I did this on a working machine, I could see the amount of memory that the machine actually had. So it is a little bit of a curiosity that right now this thing is detecting this 4 megabytes of memory as just 1 megabyte. That might lead you to believe right away that there's some type of an addressing problem with the address lines getting to the RAM that makes it only see these as 250 kilobit memory modules as opposed to the 1 megabyte each that they actually are. We're still gathering evidence on what's wrong with this machine, and I think it's too soon to jump to any conclusions on what might be wrong based on the 2 diagnostic results that we're seeing. We're seeing the initial power on data bus failure of those first 24 bits, and then we're also now seeing that it's not sizing the memory correctly. What we need to do though is to keep gathering evidence about what the symptoms are on this machine so we can actually form a proper hypothesis of what might actually be wrong. So next, I think we're going to run a data bus test. And remember, to do that, you need to specify a memory address for it to test. So we're going to copy that string there, and I'm going to put in the test sequence that you need to run to actually do a data bus test. So if you paste both of these lines, what you're going to be doing is you're going to be doing a data bus test against the very first address in RAM. So we paste this in here. Okay, the test is finished. We have the *T and we type *R, and we are getting exactly the same response as we were getting when we powered up the machine. And again, if we're using the calculator, that is telling us here that all of the bits that are in error are these bits here from 23 all the way to 0. And it's saying that these top 8 bits are good, which is good. That's matching exactly what we got from that power on diagnostic. Although notice it doesn't have that extra E at the end here because I think this is a manually run diagnostic, so it doesn't have an error code telling us what failed on the boot time diagnostic. All right, next up, let's try this extra RAM test. Recall a moment ago that I mentioned that this mod 3 RAM test doesn't seem to actually do any kind of testing, it just fills the memory with something. So let's just start with this extra RAM test here, which I know actually does work. And you'll recall, to run the extra RAM test, we have to specify 2 values for the actual range of memory that's going to be tested. The first one you type is *0 and the start address, 00000000, and then the end address where you type *1 to specify the end address, and we are going to give this just something random, like we're going to test the first 64K of memory. And then the test sequence itself is test number 6. It's going to run 1 time, and whatever, the parameter of 1, whatever that means. That doesn't seem to really matter. And what I'm going to do is I'm going to first clear the response code, because remember I said when you run these tests it seems to AND the response with what was there before, so I want to make sure that it erases it all. And we could just test that by typing *R. There it is. And now I'm going to paste this in. And this should run very quickly because we're only testing 64K of memory. And now let's look at the response code and take a look at this. This response code here works exactly the same way as the data bus test, where it's telling us which bits are good, which are zeros, and which are bad, which are Fs. And of course, if we load that into here, it's telling us exactly the same thing, that it's the same set of bits. Now you might be thinking, we have both a RAM test and a data bus test that both are pointing to the fact that that lower 24 bits of memory is not working. Now, I wouldn't begrudge you for thinking now, after all of the results we're seeing, that it's these lower 3 sims, the lower 24 bits are just bad. But there's more evidence that we can gather to see if that's really the case, pointing to these being the problem. It turns out that with the diagnostic platform here, there are some commands you can use to actually read and write directly from the memory. As in, you can put bytes of memory into RAM and then you can pull it back. I've done this kind of testing all the time in diagnostics on other machines because it's a very useful way just to troubleshoot the RAM subsystem to see if it's able to read and write from the memory correctly. Now, the relevant command is *D, and I know the original response or command was get data, but the reality is what this is doing is actually writing data into RAM. And then there's a separate command here, *M, which is what reads back the memory from RAM or ROM or really anywhere in memory, and it prints it to the serial console. Now, what you have to do when using these commands is you have to first specify the address you're going to load data into, and then you have to specify with this *B the number of bytes that you're going to be putting in. So let's use Notepad to write out the commands that we're going to use to try to store some data into memory and read it back. So first we're going to use *L, which is the command that tells it where you're either storing data or reading it back from. And we're going to be doing that all from just the first address in memory. Then you got to specify the byte count. And because this is a 32-bit system, we're going to be saving 4 bytes, which are 8-bit each, into the memory location. And then we're going to be using the command *D, which is going to be storing a 32-bit value into memory. So let's do AABBCCDD. That's a repeatable pattern, that's kind of obvious. Now to read it back, what you need to do again is specify the same 2 parameters with the address and the number of bytes, and then you simply do *M, which is going to print those 4 bytes that it's read back from memory. Let's copy and paste this. So first I'm just going to paste that in. And there you go, LBD, which is correct. That's telling us that it was able to, well, It doesn't tell us if it actually stored the data, but at least it accepted those commands. And then we're going to do this, which should print out what's stored in memory. So we'll paste this, and there it is. AABBCCDD. Now this is really curious, isn't it? Remember, the RAM test failed, telling us that in that first 64K of RAM, there was a problem with all of the lower bits of the RAM, which would represent these here, BBCCDD. And yet, clearly I was able to store that data in the RAM, and then we were able to read it back. In addition, when we did the data bus test on this exact address, this address all zeros, it told us for that specific address that the lower bits of data, specifically where we stored BB, CC, and DD, were all bad. So is it bad or is it not bad? Well, one thing we can tell for sure is clearly the CPU is able to talk to that RAM to some extent. It's just for some reason, whenever we do data bus testing, it seems to fail out on those bits. What's going on exactly? Let's do a little bit more testing here just to see if that part of the RAM really is working or this was some kind of fluke. First, let's change what we're going to save into memory to something totally different. So we're going to store this in RAM, and we'll paste this in, and let's read that back. Let's make sure that it is able to see. Yep, there it is. There's the new string that we just wrote into memory. So absolutely it's working. What we can do is we can change the address that it's saving to and reading back. And first what we'll do, let's look at the address 10 there. It's 10 hex. And okay, it's coming back as 0 and all Fs. And I think that comes from that RAM test that we ran on this part of the memory earlier. I think that's left over from that. But what we can do is let's store this data in here and let's read it back again. Let's see what happens. There it is. So address 10, when we run the commands from the ROM, are able to read and write to the memory, all 32 bits of it. What the freaking heck is going on here? Now back on the example tab on my spreadsheet here, I actually put some more stuff in here. With the help of my friend David Giller, he wrote some 68,000 assembly language programs that we can load into memory using this load mechanism, the same one. And we load this hexadecimal strings, and then we can execute that code. And what I asked him to do is write a little program that either fills the VRAM, the video memory that is, with all white, with all black, or keeps looping and does a little bit of an animation. And that's what these sequence of commands right here will do. So it sets it to ASCII mode, it loads it into that first location of memory, that's where it begins loading, it loads 18 hex bytes of data. Here is the actual data itself, that's that little assembly language program, and then this G command starts to execute that program. So if we copy this and we paste this into here and we hit OK, it doesn't say anything else besides the G there, but this should be running. So I'm going to switch over to the video output that we're going to be seeing from the Mac. Now remember, it's still flashing because there's still that problem with the video, which I haven't looked at or tried to address yet. And there it is. Now what I'm going to do is I'm going to call up the menu for the RGB to HDMI, which will kind of stop the flashing. And I think what you can see there is that the video RAM is freaking working on this machine, because the pattern you're seeing there with those lines that are moving, that is exactly what it should be doing when this little program is working. I've run this on a Mac SE30, of course, that has no faults, and I can confirm that that's exactly the pattern we should be seeing with this particular little assembly language program. So what's really cool, as just a side note, is if your Mac is not working, you can actually boot it up and run this little program just by copying and pasting that sequence of characters, and you can test to see if the video memory on your Mac SE30 is working properly or not, simply from this diagnostic console. You don't need the TechStep or anything like that. It just freaking works. Now I'm gonna have to reboot the computer here, or to exit out of that program. And let's run *A again. So what I want to do next is I want to actually run the extra RAM test, the one that actually does test the RAM, against the video memory. Now over here on the critical test, if you scroll down, I have some samples of different amounts of memory. This one right here, if you copy these two strings and you paste them into here, then that will set the start and end that is just the video memory buffer itself. And now if we go to the extra RAM test and we take this last string here, which is the actual test itself, and we paste it into here, did you see that? Did you notice how the video RAM flashed? There we go, I did it again, and I did it again. I did it 3 times there. That is the visual representation of what this simple RAM test is doing, which seems to just be simply writing all zeros and then all Fs, or all ones, into the memory and checking to make sure that that's working properly. It's a pretty simple test, and it's really not that good. We really need to write a better RAM test for the SE30 here, or figure out how to use these other RAM tests that exist in here. All right, so that was a little bit of an aside. What I really wanted to demonstrate was that when you stored programs or data in RAM, it works. We were able to run programs from memory, and there's no way that would possibly work if I say took out the lower 3 sims and we only had 8 bits of memory in there. Anytime you would read and write into the RAM, you would lose all of the data that was stored in that first 24 bits, and all we would get is that last 8 bits. But clearly, all the RAM is working because we're able to store assembly language in there and run the code. So we're able to read, write, and the CPU is able to run code right out of the RAM, even though we're getting this weird data bus error. So that got me thinking, what exactly is generating the data bus error? Is that coming from the CPU or the chipset, or what exactly? So I went to the Motorola 68030 manual and I started reading through it because I actually don't really understand that much about the 68030 system. I know a lot more about PC architecture and of course 8-bit stuff. And I came to the conclusion that the bus error, or BERR, active low signal, is actually not generated by the CPU, as the bus error signal indicates an invalid bus operation is being attempted, or when used with halt, the processor should retry the current cycle. It seems that this actually comes from the chipset, which on the SE30 is the main glue chip. It's the large PLCC chip. And we can further confirm that by taking a look at this signal list that shows bus error. The BERR is an input for the CPU. It is not an output. So this tells us for some reason the chipset on the motherboard is thinking there's a bus error anytime we try to write to that lower 24 bits of memory, even though the CPU itself is having no trouble communicating to the memory because, as we showed, we're able to store and read back the values from RAM without any issues whatsoever. So I've started thinking about the evidence we've collected so far, and the one thing I keep coming back to is that the bits that say they're working are the top 8 bits, the same ones that are used to communicate from that 32-bit processor to all the 8-bit peripherals on the motherboard, like the VIA chips and the sound chip and stuff like that. And when we take a look back at the 68030 documentation, there are these signals called transfer size signals, size 0 and size 1. And when we take a look at the microprocessor block diagram, we can see that these signals are outputs from the processor that go to the rest of the motherboard. And when we take a look at the description of these signals, it says this indicates the number of bytes remaining to be transferred for this bus cycle. These signals, together with A0 and A1, define the active sections of the data bus. Aha! The active sections of the data bus. So recall, just a moment ago, I mentioned that the bus error signal that is halting this computer is not generated by the CPU, but it's generated by something outside of the CPU, namely the glue logic chip, which is the main chipset on this motherboard. And it's these two size signals that come out of the CPU that go to probably the chipset to tell it how many bytes are remaining for any data transfers. So, and what if hypothetically there's a problem with these signals coming from the CPU getting to that chip, the glue chip, that are somehow telling the glue chip maybe it's stuck in 8-bit mode, so all the glue chip is ever expecting are 8-bit data transfers, which is why it's always telling us that that top 8 bits of memory are the only ones that are good and the rest are all bad. And it goes back to that earlier diagram I showed that says that whenever you have an 8-bit peripheral on an 020 or an 030 processor, you need to use those top 8 data bits. So this right here is a really, really good lead. So I think the next step I need to do is we need to break out the schematics for the SE30 and look to see where those size signals are coming and going, so coming from the CPU and going to where exactly, and hook up the oscilloscope to actually see if those signals are actually making their way to the destination. All right, first thing we need to do is find the size signals. So what I'm using here, by the way, are recreated schematics for the replica board that exists for the SE30. I didn't have this in the last video, but this is much easier and clearer to see. Here are the two size signals. So size 0, size 1, this is the CPU, and they make their way over here to page 3. What it does not say over there where we saw that trace going is that trace also makes its way over here to this set of connectors here, which is actually the PDS, or processor direct slot. And the reason why I want to see if the size signal's over here is because it's easier for us to probe into the PDS slot as opposed to going to the bottom of the motherboard to try to probe the CPU. So you can see here we have all the address lines, all the data lines. Pretty much we're going to have every single thing that's on the CPU on the PDS slot and more, really, because you need to be able to replace the entire CPU by plugging a card into this slot. So sizes are going to be here. There's size 0 and there's size 1. So we're talking about pin 49 and pin 9. All right, starting off, I am in pin 9, which is the size 1 pin. And I'm not seeing any activity on here. What I'm gonna do is hit the reset button. Okay, so I wanna get this displaying stuff here. So let's hit this again. Okay, so that's what it looks like when the system gets rebooted. If we move over to the next ping, which is size 0, that's what it looks like right now with the machine idle, and hit reset, and that's what we get. Okay, cool. So that's the known signal that's actually coming out of the CPU, and that looks good. I'm gonna say there's nothing wrong with the CPU itself, because theoretically the CPU might not be generating those signals correctly, but clearly it is. All right, so let's find out where this is going. So it's going to page 3, and here's page 3, and here is the main glue logic chip. So this is the main chip on the SE30 that sort of does everything. And let's see, where is that size stuff? There it is, size 0 and 1, comes from page 1, and it goes into pin 70, and it goes into pin 73. So pin 70 is size 1. Remember, size 1 was the one that was only active when I hit reset, and size 0 was the one that was sort of active all the time. Okay, I'm on pin 73. Okay, well, right there, that's a problem. We know the signal is good coming out of the CPU, but take a look at that. We can see that same sort of pattern there, and if I hit reset, you know, it's like it's trying to do it, but something's not driving that signal correctly. And I'm on pin 70 now on the glue logic chip, and this is size 1. And when I hit the reset button, there is that signal correct. So everyone, well, I think we have a broken trace. We saw that that signal, size 1, or size 0, I'm sorry, was perfect on the PDS slot, and it certainly wasn't going into this PLCC chip here. And I think what that does is it causes the main chipset to think that all these transfers are only 8-bit transfers as opposed to 16 or 32-bit transfers, and therefore when the diagnostic test is running for the data bus test, well, it's failing because the CPU knows that it's trying to read 32 bits of data from the RAM, but the chipset thinks it's talking to an 8-bit peripheral. And there's a bit of a miscommunication there in the signaling that goes between the CPU and the chipset. Freaking smoking gun, everyone, smoking gun. And on that cliffhanger, I'm gonna have to end this video here. I know people will be disappointed because I made some really good progress diagnosing this motherboard using this fantastic new information on the diagnostic mode, but there's still a lot more repair that has to be done to this board to get it fully operational, and it would make this video like 2 hours if I had it all in one part. I hope you found this new information on the diagnostic mode lurking within every Macintosh computer interesting. I know for me, I've been working on Macs for years and years, and I had absolutely no idea that this pretty comprehensive diagnostic system was available simply over the serial port the whole time. I am hoping that this information will make it much easier for people to try to figure out what's wrong with their broken Macintosh motherboards, especially ones with subtle and difficult to troubleshoot startup issues where they can't even get to a booting system. The next thing we really need to do is take the information which I put in the Google spreadsheet and start to enhance it and test it against different types of Macs. See what commands actually work on different levels of Macintoshes, because I have a feeling the stuff like the Mac Plus or the Mac SE, if it even supports the mode at all, is going to be even more simplistic than what we have going on the SE30. So I'm really looking for help from the community to take the information which I presented here and really run with it and expand on it and make it better and better so that people can do all this diagnostics on their machines without any expensive tools and armed with the knowledge of how it all works. Anyhow, in the next video in part 3, I'm going to finish troubleshooting this motherboard, hopefully get it all operational, and then eventually I will have to get back to the motherboard I gave 12 volts to, which is this one in my left hand, and we'll see if we can get this thing working using this new diagnostic mode as well. And I guess that's going to be that for this video. So huge thanks to my supporters. Their names are scrolling up the side of the screen. They make it possible to do it full time. You can now become a supporter either through Patreon or YouTube membership. So there's a link down, I think down below near the description if you want to join and become a YouTube member. I post the same stuff on both, so it doesn't really matter which one you join, but the option is there if you want it. Hit subscribe if you haven't already. It really helps me out. That one click really makes a big difference. Comment down below all the usual YouTube junk. And that is going to be that. So stay healthy, stay safe, and I will see you next time. Bye. I'm waving with motherboards.